pulled up. All right. So on Tuesday, we ran our normal linear model. We pulled up our summary. Looks something like this. This is all nothing new. We also pulled up our standardized betas from that linear model. And we we specified our first model, which we'll just call model A, and then we actually fit the model with our sim function, telling it that to fill in missing data with with full information maximum likelihood estimation. And as a reminder, this fixed.x equals false just tells us to give us the correlations in the output. And so that brings us down to now actually looking at the information from our model, which we'll do using the summary function. The specific arguments that we're going to include in this is fit measures equals true, standardized equals true, and RSQ, which is R squared, equals true. Fit measures equals true. We'll just put in a lot of different fit measures. In fact, for the ones we're concerned with in this assignment, it gives us all of the ones that we're interested in except for one. It doesn't give the NFI, which is why we'll use a fit measures function down here later on. Standardized equals true just gives us the standardized betas in the output. If you leave that off, it won't report those standardized. And then also R squared, we just want it to include the model R squared in our output. So when we run this, it gives us a lot of different information. Up here at the top, it has information about the model itself, including some fit measures and stuff. And then down here is where it gives us some covariances and estimates and things like that. So we're going to spend a pretty good amount of time here in this summary output. And so on number 5, it's asking us what's the chi-square, degrees of freedom, p, and the ratio for your model. This is asking, you want to look here under where it says the model test user model, not under the baseline model. So this first part is asking us to report this here. And as you can see, our test statistic is 0 and our degrees of freedom are 0, and it doesn't give us a p-value because the p-value is not a thing here because rather, let me ask, can anybody tell me why we have 0 as our test statistic in degrees of freedom and we can't get a p-value from this particular model? Excellent. Exactly. It's just identified. You could think of it as perfectly fit. So obviously then our ratio of this will also be 0, but that'll change once we get into some later models. As far as when we move down here a little bit where we have some fit information, the homework asks you to give the CFI and the NFI. The CFI is in the summary right here where our CFI is 1. The NFI is not. So to get the NFI, we'll run fit measures, and we'll just get the fit measures of the model. And what I wanted to show here with these two different commands, if you just run fit measures, it'll just output all your fit measures like this. But you may not know necessarily what all these different things are. If you include output equals text, it'll output it this way instead, so it gives you all the same information, but it will actually tell you instead of NNFI, that's the Bentler Bonnet non-normal fit index. So just including output equals text is what outputs it this way instead of this way. But that said, we're looking for our NFI here, which we see is also 1. Anna, do you want to talk about these things as we go, or do we want to go over like each of these different things and then go back to kind of talk about the specifics of what each one are?
Let's go ahead and talk about them as we put them in. So we had a chi-square value that was 0, with 0 degrees of freedom, and we couldn't get a p-value. What are we looking for with chi-square? What are we hoping? Good. Yeah, we're hoping that it's not significant. Now, in this case, of course, we can't actually evaluate the fit of the model because it is just identified, meaning that we're estimating exactly the same amount of information or parameters as what we put into the covariance matrix. So we can't really say anything about model fit from this perspective. The next thing we were looking at is the CFI and the NFI, both of which have the value of what? Yes, they're all 1. And what are we hoping for to indicate good fit in these indices? Good. Yes. So some people will go with a more, sort of liberal 0.9. Some people go with a little bit more of a conservative 0.95. The higher, the better, and they max out at 1. Of course, because these are based on chi-square, they are also 1s. So they're, again, indicating a perfect fit, but not super informative in a just identified model. Okay, let's keep going, Austin. Thank you.
All right, so then the next thing that we're looking for is the RMSEA and 90% CI, which that we find up in our summary. If we scroll back up here, so when we print our summary, if we scroll down just a little bit, we will find our RMSEA here, as well as that 90% confidence interval and the p-value. Once again, we see in this case it's 0 because once again we have that just identified model. Also, go ahead.
So for RMSCA, the p-value, we also want it to be like chi-square, not significant, because we want basically to be saying that the residuals or the errors of approximation we're making are not significantly large. But of course, here again, because it's a just identified model, we cannot get good fit information. It just provides you perfect fit because you gave it no other choice. It's like going to a road, down a road, and the road is only straight and there's nowhere to turn, and then people say, oh look, you chose to go this way. It's like, well, I had no other choice.
For the number of iterations that it took, just as a reminder, we talked about this earlier this semester, where under the hood, basically the software is trying a whole bunch of different things, and to converge on something is to kind of settle on, okay, this is a good I don't know what you call it, a good thing to settle on right here. And how many times did it have to try something before it decided, okay, this is a good model or whatever? And that's up here at the very top. This tells us that this particular model ended after 61 iterations. Now, as far as the number of iterations go, the fewer iterations that you have, the more stable the model is said to be. I don't really have even like a rule of thumb as far as with Levon what is considered like good or stable or a low number of iterations.
I
Sorry.
can give you some guidelines for that. So this is different than PCA. It's different than logistic regression. For all of those, we were looking for, no more than, say, 25 iterations. Once we get to structural equation modeling, it's just more complex. And so there's just more fiddling because an iteration is when you change the value of a parameter, rerun the model, and then see how well it fits. And then you take that information and you say, oh, okay, like, well, if I change this parameter, then rerun the model, how well does it fit? So it's like what we talked about in class of playing hot and cold, where you're like, you're getting warmer, okay, you're hot, you found it. And that's kind of what iterations look like, from a very non-mathematical perspective. So because structural equation models just have a lot more parameters that could be fucked with, they're going to take more time. And that means that if the model doesn't converge, say in about 250 or so iterations, then we start to worry. And I have run models before that took over 500 iterations, but once you get to like 1,000 or something, then you're like, okay, there's really model specification problems here. I need to go back and fix my model. And this is not something we're going to cover in our class, but it is going to be covered in an STM class. How do you make a model converge if it's not able to do so within a reasonable number of iterations?
Yeah, and I think I'd have to check the documentation, but I think that the default for Levon is to allow 500 iterations, and that after that, like it'll just tell you the model failed to converge, which you can change that in your summary. You can specify how many iterations to allow, but I believe that the default is 500 iterations. And Morgan's
And
asked,
so, yeah, go ahead.
well, Morgan's asking, it cut out. She was asking what that reasonable number was. If you're getting above 500, you should probably at least give it some thought. Certainly, if you're up into 4 digits, but it's not uncommon to see 200-300 iterations in these models.
And Jake made a point that he can't believe people would do this by hand. This technique actually wasn't developed until there was at least some pretty rudimentary computer software. So I actually don't think anybody ever did one of these by hand. Factor analysis, however, you can do that by hand, and that's a really good preview into how painful this can be. Okay, so we also have a question about how many, what does it mean for the iterations? Basically, once we move to SEM, if you use your default maximum iterations allowed in your computer program, so in Levon and Austin just let us know it's 500. If your model needs more than 500, that's probably a problematic model, and it just means that it failed to converge. Or at least it failed to converge within 500 iterations. What that means is that it's still, like, from a hot cold game perspective, it still hadn't sort of found a solution. It was still trying to estimate the parameters so that they didn't actually change. If that happens, you are going to have to go back and look at how you drew the model, what are you estimating? And again, model re-specification is not something we're going to cover. But what it basically means is you have to go backwards and start from scratch, maybe add a path or delete a path or do some other things. There was one other thing I was going to say about iterations, but it just escaped me. So if I think about it, I'll jump back in.
All right. Any other questions?
Oh, I do remember. If you are comparing two models, then the number of iterations a model takes to converge can be a soft indication that it's a better, more stable model. So just like when we were looking at logistic regression or at EFA and talking about, well, how many iterations did it take? Smaller is better, but it by itself is not super meaningful.
All right, so then it's asking us how much variance in reading achievement is explained by the exogenous variables. That's where we're going to be looking at our R squared, which is down at the very bottom of our summary output, where we see our R squared is 0.083. So what does that tell us about how much variance is explained? Exactly. So we got 8.3% of variance explained in SRA by these four variables: sex, birth region, mother education, and SES. Uh, on the whole, well, I guess it would help if I didn't leave the answer in there. What can we say about the fit of our model? Well, it's a saturated or just identified model, which means that it fits perfectly, which is not a good thing.
So the way I used to talk about why perfect fit or just identified or saturated, all those are the same thing. Models are actually not a good thing. On the surface, it feels like it is a good thing. But it really, what it means is you have no choice. So we want a model that fits well when it had the option of showing us that it actually didn't like, what we put in, that it didn't actually fit the data. And so when you're thinking about model fit, you want as close to perfect as possible when there were other options, other potential models, or when the information could have been, nah, never mind, I don't fit. So I liken this to like how the difference between an arranged marriage versus one where you get to kind of select your partner. You want to be with somebody not because there was an arrangement and you had no choice, but because this is somebody that you actually like had pics of others and you said this is the one. So we don't like just identified models because it's the equivalent in stats of an arranged marriage. Not to impugn a cultural practice, but just for illustrative purposes.
So moving into the micro assessment, it's asking about which variables significantly predict or don't significantly predict, or which ones predict best. Here we're still in our summary, and when we scroll down to the chunk that says regressions, this is where we're looking. So here we have our p-values for each of these. If you think of these as that path diagram, this is basically each of our paths. And so we have our p-value here for sex, for birth region, mother ed, and SES. So which variables significantly predict SRA? Yeah, birth region and mother ed, which means obviously that sex and SES do not. And Casey says birth region is the strongest. Why would you say that, Casey? So, uh,
Actually, it is not the largest standardized data.
so when you're looking at these tables, this estimate here is not the standardized. This is the unstandardized estimate. The standardized estimates are down here at this end. The this STD LV and STD all. Really, what you need to be looking at is this standardized all. The LV column is only standardizing latent variables. And this last column is with all variables standardized. So these over here are actually our standardized things. And what you can look at is this Z value column.
So if you remember in class, one of the lecture slides talked about how to evaluate the significance of each parameter. And I had talked about how Z values that were large, absolute value larger of 1.96 were significant at the 0.05 level. If they were absolute value larger than 2 I don't remember what, for something, then they were significant at the 0.01 level, and 3.33 significant at the 0.001 level. So our largest Z value, absolute value, is 11.49, which is associated with mother ed. also the z-value of 11.49 is associated with a beta of 0.24. So standardized all is your beta.
And if we go back to pull up those standardized betas from our linear regression, what you'll see here is if you compare these to these standardized all, this column here, you'll see that you have basically identical values.
Okay, so let's address a couple of the questions that are in the chat. We'll go with Morgan's first, then we'll go with Jake's. And if you have more questions, keep throwing them in the chat. Aston, do you want to tackle Morgan's and then I'll tackle Jake's?
Yeah, so when you're looking, Morgan, at those z-scores and the standardized all, it'll give you the same information, essentially, that whichever one has the largest z-value is going to have the largest standardized beta. So regardless of which one of those you look at, you'll get the same information because that z-value is based on standardizing all of them. So if something has a larger z-value, it's because its standardized value is bigger than whatever else.
Yeah, it's fine to look at either one. Jake, typically we are going to report the results of a path analysis or a CFA or an SEM model in a couple of ways. There's the best way is with a picture, always a picture, because again, a picture in this case truly is worth 1,000 words. So if you have your path diagram, which we are going to look at in a little bit for this model, the path diagram that includes the standardized paths is probably the best way to report it. And if, I don't know if R defaults to this, but if it doesn't, you can then make your path pictures with stars and other things to indicate significance, or you can just ghost out the non-significant paths. There's a bunch of different ways to do this, and you can look at published papers as examples. Some people will put the regression information we just looked at in a table, but they're pretty hard to read because if you're not sure how to go, now we practiced it in class, but if you're not sure how to go from equations to a picture, a table is kind of the equivalent of giving somebody a lot of equations. And so you will see some people report the standardized paths and the z-values and other things in a table. I do have an article up in Blackboard about what are the reporting standards. And then the final thing is that the figures that are the most common way to report this information often include a figure note that has the overall model fit information. So your chi-square and your norm fit index and your CFI and RMSEA and so forth. Or you can report those in text.
So I didn't have the actual diagram for this particular problem in the script, but just to show you kind of what it would look like if we had, because we'll get to that on the next problem. But it would look something like this, where here's where we have our standardized estimates for each of these paths. But we'll fiddle with some of that stuff here on this second model that we're getting ready to run. So where are we? So looking at the correlations among those exogenous variables, I'm just going to rerun our summary. So what you're looking at in these is when you come to your covariances section of your summary, the standardized covariances give you your correlations between these variables. So if you're looking at the correlation between sex and birth region, you look under that standardized all, and the correlation between sex and birth region is 0.059. The correlation between Mother Ed and SES would be negative 0.212, etc. So this, including that, if you don't have fixed.f in that summary, it would basically be missing this particular portion of the output. But again, looking at those standardized covariances gives you those correlations, so you can pull from there and put them into a standard correlation table. The other part of the summary where it gives our intercepts here. So when we look at our intercept of SRA, part D. Part D, Josh, is what we already did. That's just looking at comparing those standardized all to the standardized betas from LM. So when you run either PSYC or LM beta with the LM beta function, it gives you the standardized betas. There we go.
Yeah, the basic gist here is we wanted you to have the experience of running one of the most basic path analyses you could draw, which is really just a regression, something with 1 dB, 4 IVs. Run it the way you know how to run it, through linear modeling, and then run it through path analysis, and basically to show you that it's the same fucking thing.
Yes. So looking at this intercept, the intercept of SRA is 33.334. What does that number mean? Exactly. When everything else is 0, the predicted value of SRA would be 33.334. And then what is the research question that this particular analysis is answering? So change in SRA is a function of the other variables. What's the best predictor of SRA? If you want to be a little more specific with it, we're asking about demographic variables here. We're asking about the sex, their immigration status, their mother educational attainment, and their socioeconomic status, and asking, how do those predict reading achievement in these middle school children? Does anyone have any questions before we move on to our next model? All right, so in the next model, we're going to look at how school achievement, operationalized as SMA, SRA, and GPA2, how that relates to educational attainment and job status. Josh is asking if there would be any mean centering going on in these models, and the answer is yes. That's part of the standardization process, that everything gets centered and standardized. So for number 7, in terms of specifying our model, so we have GPA regressed on or predicted by SMA and SRA. Education 3 regressed on SMA, SRA, and GPA. And job score 3 regressed on education and GPA. And then here we are explicitly adding in the correlation between SMA and SRA with this double tilde. So Jake is asking, so then the intercept would actually be SRA when everything was standardized, centered, and not at 0 for the last one. No, not so much. I should have been more careful with my wording. Those standardized betas, which are what we're looking at in terms of these. So when we look here at this particular path diagram, and we have 0.04, 0.1, negative 0.15, 0.2 something or another, and 0, those are standardized, so they are centered. If we look at just the unstandardized estimates here, that would not be with things zeroed or centered. Does that make sense?
Typically, we don't mean center variables before we run a path analysis, like in our data frame, unless we're going to create interaction terms, in which case you probably mean center first before you create interactions to reduce multicollinearity. But there are way cooler ways in SEM to do moderation than to do mean centered and interaction terms, which again, we're not going to cover, but oftentimes it means that people don't mean center variables.
So here we've specified our model B just as this character string. Here, once again, we fit it with the SEM function, and we'll call this mod PA2. And now I'm going to break this down a little bit to, I'm actually going to take that off. So we can expand this out, because we're going to play with this sim paths for just a second to look at what some of these things do. So if I run what we have in the script for sim paths for this model, so this what, the argument here, and here it says paths. What that's telling us is that we don't want any sort of numbers on here. Like, it is just showing the actual sim paths is the library, or sim plot library. And Morgan, which is not available? Sim paths or sim plot? We'll come back to that.
Yeah, let's take just a minute, and can you guys throw in the chat if you were able to run the sim paths, and we'll make sure that we have everybody in the same space. Quite a few of you are able to run it. Becca says hers didn't have an error, but it didn't show up either. Austin, you need to work some magic there. I'm pretty sure that we can all screen share. And so if you want any student to screen share, Austin, I have it now so that multiple participants can share.
It may not be an issue that the error didn't pop up. All that warning is saying is that it switched some stuff under the hood, because sim paths is not in the Lavon in the Lavon library. It's a separate thing. So Becca, just let us know if you're not seeing what we see as far as the actual output and the results. Don't worry so much about the warning messages.
Yeah, Becca was the opposite. She didn't get a warning message, but she cannot see it.
Oh, but didn't show up either.
Yeah, Becca, do you want to try to screen share and maybe start with Becca, and then if Isabel wants to, we can just see if we can figure it out? Yeah, if your R is pretty old, it might just be that.
So Isabel, it looks like uh, it says that there's no package called huge. Let me look over here. So try to install that huge package manually first, and then try to reinstall Simplot.
And you guys are all running R versions that are earlier than 3.5.2?
And we should be able to get it. We should be able to get it, because even if you have an older version of R, like this has been around for a while. It's been around for a few years. But so if you aren't able to get it, and this is why it's important to make sure that you're reading the console, because oftentimes these things will tell you what's wrong. For instance, when it says like there's no package called whatever, then your first step is going to be to try to install whatever package was missing separately, and then install whatever you were trying to run. Since this is all already laid out, all the code is already there and whatnot, and because the SimPath stuff is not terribly important to what we're trying to do, as far as this is what Ann and I have said, that there are better ways. Like this gives you a decent, like quick and dirty type thing to help you understand your output a little bit better. But if you were going to be making a plot for publication, there are other better ways to do it. And in that interest, I'm going to go ahead and move along. For those of you who don't have it in, if you're not able to get it, like we'll figure something out. You can shoot me an email after class. We can arrange a time and try to get it all figured out. And plus, this is being recorded. It'll be uploaded right after class, and you can go back and play with it. But so for the what here, right now we have paths in there, which tells it we just want the actual structure itself. If we change that to STD, then that gives us our standardized path estimates of everything. If we change it to EST, that's just our unstandardized estimates, and you notice that everything kind of fades away, because by default it has a it fades based on the strength of whatever. But if we include fade equals false, then it doesn't fade it. So the reason that these all went away is because these are really, really tiny, unstandardized estimates. These things like the layout, if we run it as just tree, it does it's all the arrows and everything are connected the same way, but it just gives a different visualization of it. The rotation just has to do with which way it's oriented. So if we do rotation 1, it does a top down. Rotation 2 does sideways, etc.
Actually, this lets me jump in real quick about something I failed to mention in class. So there are two conventions for the order in which things go in your drawings. And the order that I have been presenting and that you guys have been sending me with your scribbled drawings, which have been great, by the way, is typically left to right. So the earlier variables appear on the left, just like if you're reading, and the downstream variables, so the arrows are always pointing, originating on the left side and pointing rightward across the page. The other conventional way you see this is top down. So the earlier variables or exogenous variables are near the top of the screen. And then as you're going, the arrows will be basically pointing downwards, the one-way arrows. You will not see, by convention, left to right, right to left, and you will not see bottom to top. That is really violates the expectations that people have for glancing at your picture.
Um, for the residuals, I have residuals equals false here. If we change that to true, it's going to add in our error terms. That's also related to this style equals literal. And if we take that off just to have the default style, it's going to change our those residuals where it just has this arrow looping back on itself. Um, and then our intercepts equals false. If we leave that as true, it also puts like indicators for the intercepts on things. But again, like I'm just trying to make a pretty picture, and so these things that like the defaults that I've put into the scripts for the various sim paths will give you what we want you to see. But again, there's a lot of stuff, a lot of different options that can go into these things. I mean, you can even manually specify where in two-dimensional space you want each of these different boxes or circles, ovals, whatever to go. I put that link up at the top of the script to the SimPaths stuff online that you can look to see what all's in there. But for today, all we're going to be worried about is looking at the specific stuff that we have in the scripts. And so in this case, we just wanted to see the structure itself and not yet the coefficients, the estimates, or anything like that.
Jake asked a question, it's a good one, which is, can a variable be both exogenous and endogenous? For example, in our path diagram here, we have GPA being predicted by SRA and SMA, but it is also predicting education 3 and job score 3. And so in the real sort of like true version of SEM, the only thing that defines an exogenous variable is one that has no one-way arrows pointing to it. So no one-way arrows pointing to it. From that perspective, there are only two exogenous variables in this model. Now, endogenous variables can, in fact, also predict other variables in the model. So I like to call them swinger variables. But they are, from a strictly speaking perspective, they are still endogenous because how they came to have their value, how they came to have their score, is thought to be a function of values from other variables in the model. So the other thing that's tricky about this, so from this perspective, we have 2 exogenous variables and 3 endogenous measured variables, and then of course we have our latent error terms. The other thing that's tricky, though, is that I told you that R automatically adds covariances between latent endogenous variables, but not latent endogenous variables the way that I just defined them for you. It only does that if the variable has one-way arrows pointing to it and does not serve as a predictor for anything else. So from R's perspective, there's only one truly endogenous variable in this model, that's job score 3. So it is not going to create covariances among the residual terms with the 3 endogenous variables. We'll see in another model how it will start to do that unless we tell it not to. But from this perspective, we have 2 exogenous, 3 endogenous, but only one that is truly only functioning as endogenous. It's kind of a confusing thing. If you're writing this up, you would describe this model as having 2 exogenous measured variables and 3 endogenous measured variables. Or 2 exogenous measured variables, 2 mediators, and 1 endogenous. You could say that as well.
And then Nia, even though you said never mind to answer your question for everybody, as far as showing the residuals for just the endogenous variables, you can see that's I have that up here. When I turn the residuals on, residuals equals true, and if you have style equals literal, then it will just give you those error terms for those 3 endogenous variables. If you turn on your residuals but take off this style equals literal and just have that default style, it'll automatically give you those residuals for everything on there.
But it's a little bit weird because they're not actually residuals for exogenous variables. They're
right,
really just variables.
Right. Yeah. So then moving on into now like getting our information from assessing the model itself. We've specified the model, we fit the model, we have our path diagram. So now we look at our summary just like we did before. So what is the sample size of this analysis? $2,314 observations exactly. How many manifest variables are in this model? Josh says 2. Does anybody have different opinions? Casey says 5. Lauren says 5. Good. Josh, can you think of what you're missing as far as saying that there's 2?
Yes, anything that is measured, meaning it's a variable in your data frame, counts as a manifest variable.
And so how many latent variables do we have in this model? Exactly. Even though technically they're not visible on this path diagram here as it is, we could make them visible. If we switch back to here, now those are visible here, here, and here with those error terms. So now what is the chi-square, degrees of freedom, and p-value for this model? Yep. And it looks like Josh caught it. What we're looking at here as a reminder is that the user model, not the baseline model. So our chi-square, we would report chi-square 2 degrees of freedom equals 15.93. P is less than 0.001.
So this is very tricky. You do want to make sure that you're looking at the user, meaning that this is the model you specified as the user. The baseline model is a model that assumes there's no paths at all. So it's basically a blank model with just 5 boxes and nothing else, or what we call the stupid null model.
And for our CFI and NFI, we can get our CFI here in our summary. And as a reminder for that NFI, we need to check our fit measures. So we have our CFI here and NFI here.
The chi-square to degrees of freedom ratio, is that actually in any of the output, or is that just something you have to hand calculate?
They'll just have to calculate. Sorry, I forgot to mention that.
So chi-square was 15.93 and degrees of freedom was 2. So you just need to divide those two, meaning that it's about almost 8.
And then, so CFI of 0.996, NFI of 0.995. What does that tell us? Yes. As Josh says, those are good. For our RMSEA, we're back up in our summary, where now we don't have 0.
What are the values we're looking for RMSEA to indicate good fit? Yeah, Jake got it. 0.08 or lower. Some people are more stringent, as Casey noted, 0.05 or lower. And so look at our RMSEA value and think about it in light of those requirements. How are we looking from an RMSEA perspective? Yeah, we're looking pretty good. Another way we know that we're not making a lot of error in approximating the data is because the p-value associated with RMSEA is not significant. So that's good.
How many iterations did it take to converge on this particular model? 76, yes, right here at the top. And then, what can we say overall about this model?
Josh says overall it looks pretty good. What do others think?
Josh says, oh, wait. Non-significant chi-square, correct? Yes. So that's the RMSEA and the fit indices. Seem to suggest like, oh, maybe this isn't so bad, but that chi-square and chi-square degrees of freedom ratio isn't really what we're looking for. So overall, like this isn't a particularly great model.
Yeah, this is a mixed bag. So there, it is often the case, as we discussed before, that chi-square will be significant, but that's especially true when the degrees of freedom are large and when there's a pretty complex model. So we like chi-square to degrees of freedom as another way to think about chi-square, because if it's in that 2 to 3 range, then even if P is significant for chi-square, we're still like that plus the CFI, the MFI, the RMSE, all those things, we're like, actually it's pretty decent. The problem here is that our chi-square to degrees of freedom ratio was quite a bit larger than 2 or 3. It was around 8. Our chi-square was significant. We did only have 2 degrees of freedom, so it wasn't like it was a very complex model. So we have kind of a mixed evidence for model fit. And probably there are some things that could be done here to make this a little bit better.
Uh, Moving into now looking at our estimates. We're going to scroll down in our summary into our regressions. So, which variables are a significant predictor of? Shit, I left the answers in here again. uh, Significant predictors of GPA 2. So we come down and we look at our GPA regressions, and we see that both of them are significant predictors, SMA and SRA. For education 3, we look at that portion of our regressions table, and we see again here in our p-values, all 3 p-values are less than 0.001. Just a reminder, p is never actually 0. If it ever says 0, what it means is less than 0.001. And then for job score 3, again, looking here, we see that all of or both of our predictors are significant. For looking at which is the best predictor, I'm going to run that summary again just to try to get my standardized stuff on the same lines. So here, looking in terms of what's the best predictor of any given thing, where it says like that critical ratio, like that thing of the z-value column, or looking at those standardized estimates. And so what's the best predictor of education 3? When we look here, we see that GPA 2 overwhelmingly has the largest z-value, also has the largest standardized estimate over here. So that will be the best predictor of education. Where do I find the correlation between SMA and SRA? Under covariances. And so what is that correlation between those two variables? Exactly, 0.61. For the intercept of GPA 2, what does that intercept right there tell us? Josh says a 1 unit change. We're talking intercepts here. Yeah, there we go, Nia. Nia says it's the predicted GPA when SRA and SMA is 0. And it's important to point out that that's when SRA and SMA are 0, not when all the variables are 0, because when we look up at our regression table or over here in our diagram, we see that GPA2 is only predicted by SMA and SRA. We don't have GPA, education, or job score. So that intercept, when for somebody who has 0 for SMA and SRA, we would predict their GPA at time 2 would be a 1.48. For the R-square values for all of our variables, once again, we're going down to the bottom of our summary, and it will just give us the R-squares for each of the 3 variables. And so we know that we're explaining about 27% of the variance in GPA2, about 15% of the variance in job score, etc.
So the last 2 questions for that section ask you about what's the research question that's being under analysis here, and to paste your path diagram into the homework assignment. Austin, this isn't part of our homework assignment, but that's because the homework assignment was originally written with Amos in mind. And I wondered if we could do a quick thing before we do number 11, and that is to run that argument that allows for modification indices. Because here we have a model where it's clear that the model has some evidence of good fit, but also some evidence of not great fit. And so in our homework, I said, well, let's see if we can just add some shit, right? Let's just add some paths. But instead of just deciding kind of like, well, maybe this or maybe that, we can actually ask R to tell us exactly what could be done to make this model better. Now, when we're doing this, we're moving from what kind of an analysis to what kind of analysis from a theoretical perspective. Perfect, Cameron, exactly. We're moving from confirmatory to exploratory. So we're now in hypothesis generation mode. We have to be very careful. But because we have hypothesized and specified a model, and we have some evidence that it's not doing a great job, if that happens to you, this is probably a next step, which is, okay, well, data, tell me, data like as in Star Trek, but also as in your real data. What do I need to do to make this better? And Levon can give you information about that by running the mod indices argument. And then maybe Austin, you can walk us through how to make sense of all this.
Yeah, so whenever you run just this mod indices and give it mod PA2, the things to look at, this EPC here, that is the expected parameter change. And so basically, let's say, find a real small one here, GPA to job score 3. So if I expand this graph out a little bit, GPA to job score 3 is this particular path right here. And this tells us, this expected parameter change tells us that if we take out that line right there, it's not really going to change much about the outcome of this model, that we're not really losing much by taking that out. And so if we did take that out, we're saving ourselves a degree of freedom without really losing a lot of information. Whereas if we take out the job score 3 SMA line, I guess that's an indirect line anyway, or the covariance there between those two. Here, the SMA job score 3, again, damn it. Well, I guess the point is that this is kind of like the when we did the reliability, and there's the table that has the alpha if dropped, and so we can say, if we drop this item, the reliability goes up to zero point 0.8 or whatever. That's kind of conceptually what this EPC column here is telling us.
Okay, so the MI column here is actually what is called the modification index. And the EPC column as expected parameter change column is where you really want to be looking. And so on the left-hand side, for example, I don't know if I can actually draw anything. I don't think I can. At line 20, you have GPA 2 tilde tilde job score 3. And what it's telling you is if you add a covariance arrow between the error terms associated with GPA 2 and job score 3, I'm sorry, not a covariance. If you take out the path between GPA 2 and job score 3, your estimated parameter change is going to go down. This is the chi-square change, okay? It's going to change by 1.48, but that's not a big change. So it's basically saying I'm not going to lose a lot if am I doing this right? I might be doing it wrong. I think it is between the covariances between the error terms for that one. And that's a way that I can improve model fit. But if you look at EPC, you want to look at the largest positive value. Negative values tell you what to take out, and positive values will tell you what to add in that's not already in the model. So when you're adding in, that's called the Lagrange multiplier. And when it's telling you what to take out, that's what we call a walled test. So from this perspective, what can we add to our model that would have the biggest benefit? Yes. Drawing a direct path from math to job score will give us the best benefit for improving model fit. Right now, the way that math influences job score is entirely thought to go through these other two intermediate variables. But this statistic is telling us that if we add a direct path from math to job score, we're going to do a much better job. Now, what I had said in the homework was we might think about adding achievement, direct paths from reading and math to job score, because maybe it makes sense to think about these achievement scores as being sort of like indicators of like intelligence or some other things like this. But here is where you can look to see what you might add directly. So the question that Jake is asking is whether we're talking about direct paths or covariances. And so the 18 is indicated. Yeah, I guess they're wanting it to be a covariance, but I still think that, right, because if you look at SRA and SMA and job score, you're still getting modification indices of 16 and then, yeah, almost 4. So they do say that the best thing to do would be to add a covariance, but you cannot add a covariance between an exogenous variable and an endogenous variable. So what they're really saying is that they want you to covary math with the error term associated with job score. And that doesn't make any sense to me. Like, you could do it, but it doesn't make any sense. It makes a lot more sense to say, well, let's directly predict job score from math rather than have math predict the error term associated with job score. But yes, Jake, you're absolutely right. So you do have to be careful when you look at modification indices to make sure that you're not just blindly following whatever they tell you, but that you're using a little bit of like logic and reason as well as information from this data-driven approach.
All right, and I think we'll stop short of starting with number 11, but I want to briefly talk about this next big jumbled mess of stuff because it says to paste this, path coefficients or with your standardized path coefficients into the homework. Um, and so I have a couple different things here. This first one is just running more or less with the minimum information. And then here I run another one where I just added in some additional stuff. Specifically, I added in here pause call equals black. That's just telling it, because by default it has positive coefficients are green, negative ones are red, since they're all positive in this case. By just changing that the positive color to black, instead of this being green, all of these things will be black. Fade equals F is what turns off that automatic fading stuff. So if I throw in a parentheses here and just run it up to that point, here's what this looks like. But all of these labels are kind of tiny and hard to read. So this edge label CEX is the font. So by changing that to 1, just making it a little bit bigger. And then also here by default it puts everything in the middle, but that's a little bit of a problem when you have things that cross perfectly because it overlaps here. So by telling it edge label position equals 0.4, that just says to put those coefficients like 4/10 of the way down the line instead of right in the middle. So now when we run this whole thing, it's the same as the first one that we did, except for we're not fading, we're shifting. Instead of it being in the middle, it's 40% down the arrows, made them a little bit bigger, made them all black. Now, you can just use the export button up here. You could screenshot and just crop out this thing. But as far as if you want to programmatically export this, the way that you would do it is if I run this line here, just png, mod2.png, that will open up a png file. Now, whatever I run next, gets put into that png file. So I run that same sympaths command again, and then when I run this dev off command, that's what closes the file and saves it. So now that I've run this dev off, if I look in my working directory, you'll see a file there called mod2.png. And so I can open that up, and now I have the actual PNG file stored in my working directory. So once again, use the export button, screenshot it, but this is if you ever want to programmatically do things. You can initialize whatever type of image file you want. Whatever you run between there and running dev off is what will become the image, and then dev off is what closes out that file and actually saves it. We'll pick back up on Tuesday with our last little bit. If you want, you should basically be able to, at this point, go ahead and do the other problems in the homework. You should be able to work through, because surprise, it's going to be doing all the same thing basically. But we will be going through those on Tuesday. Does any Josh is asking if that'll work for any plot, and the answer is yes. However, I for regular plots, since I use ggplot for everything, I just use ggsave, which works pretty easily and in a straightforward way. And I know all of the specific parameters as far as sizing adjustments, DPI adjustments, all that sort of stuff. So I use ggsave unless it's something that's not a ggplot, and that's when I use this method for exporting images.
We are not going to be doing any cross-lagged analyses in this class. There's not enough time for it. You could certainly do that. In fact, you could draw the one that we did in class or some other version of one if you wanted to play with it a little bit. And feel free to come to office hours or to make an appointment with Austin or I to talk about how to interpret the results. But like I said, we're just kind of scratching the surface of the cool things that you can do. And we really want to get to CFA so that you have at least a first experience with latent variable modeling in R. So thank you, everybody. I'm going to probably annotate some modification index stuff so that you have it up on Blackboard as a way to understand. I know we went through that pretty quickly and it was not part of the lab today. So I think we're just going to run it again, annotate it a little bit and tell you how to interpret and use that information, because it is like, gives you a lot, but you don't necessarily want to act on all the information. So we will see everybody on Tuesday. We're going to finish this up and we are going to try to do CFA before the semester's over.